I didn't.
All right. On your worksheet that you got after the quiz, you were supposed to graph for the first one the cosine curve, and then graph the inverse of that. When it says reflect over the line y equals x, that's the inverse, right? How do we find an inverse from a graph? Yeah, switch the x and y and plot the new points. So for example, I'm going to put cosine up here because that's what was first on your paper. Here's the cosine curve, and what you should have done once you had this graph was on the graph next to it, if this is 0, 1, over here you plot 1, 0. If this is pi over 2, 0, over here you plot 0, pi over 2. If this is negative pi, negative 1, over here you plot negative 1, negative pi, etc., etc. And then you reconnect, and you drew your curve. How many did that? Good. If you didn't, do it now. I'm going to do it electronically here with this little applet that I have. First I'm going to fill in the, well no, I'm going to leave that. I'm going to turn on the inverse. Now, that dashed line up there, of course, is the line y equals x, and you're going to see that the blue and red curves up here, the blue curve will be the cosine function, the red curve will be its inverse. They will be symmetric to each other over that line, mirror images of each other over that line, because that's what happens when you switch x and y. So, as I drag the domain of the cosine curve to the left, you'll see the red curve appear to the bottom. And as I drag the cursor, or the slider to the right, the top of the red is formed. And you can see it's pretty cool. It forms a nice mirror image of each other over the line y equals x. What do you notice right away, though, about that red curve? Dylan?
It's not a function.
It's not a function. That bothers us, doesn't it? We like to have functions, okay? Now, it doesn't bother Evan in the least. Now, is it a problem that that's not a function?
It's a huge problem.
Talking over with somebody nearby. Is that a problem that it's not a function? Dylan? You can talk with Corey. Just like stream of consciousness. Go ahead. Dylan's just laughing for you, I'm sorry.
Well, what about?
Oh yeah, there you go. Bailey will talk to you.
Is it a problem? It's a math problem, and that's really the biggest problem we face.
I don't know how
I think
valuable
you
that
could
was.
just restrict the domain, and then it won't.
Is it a problem? That's the question.
I don't think it's a problem.
How many think it's a problem?
It seems like it's a problem.
How many think it's not a problem? All right, most people think it's not a problem. Who thinks it is a problem? Why do you think it's a problem, Darian?
It's not a function, so it's a function, right?
It's not a function, so it doesn't function.
Something to knowledge on.
Anybody else?
Well, we were saying that your calculator won't be able to handle it.
Good. All right. So here's the situation. The answer is maybe. Is it a problem? Maybe. It depends on the situation. Sometimes it's a problem, like when it's a calculator situation. Sometimes it's not, like we did at the beginning of class. Remember those 3 first problems we did? We had an infinite number of answers for each of those. That's not a function. We got lots of outputs, but it wasn't a problem. We just listed all the solutions. So it depends on the situation, which we'll get to in a minute. However, let's take a little diversion here. In mathematics, some things are discovered. For example, the concept of 2, right? 2 exists whether we know it or not. There are 2 rocks on the ground. Are those rocks self-aware? Do they realize that there are 2 of them? Most of us would say no. Somebody would say yes, they can. But my point is that probably not. But there still are 2 of them. It doesn't change the fact that there are 2 of them. That concept exists. However, did somebody discover that symbol? Oh, that's 2. No, somebody made that symbol up. So the symbol that we use for 2 was different from the symbol that the ancient Romans used for 2, which is different from the symbol that the Chinese used for 2, right? There's all these different ways to represent 2, but the concept exists. So some things in math are discovered, a lot of things are discovered, but a lot of things are made up in order to be able to talk about it. For example, the logarithmic notation or limit notation. The concepts exist, but we make up the notation to go with it. One of the other things that's made up that you probably don't think about is order of operations. That's a matter of convention. Who said that multiplication has to come before addition? Nobody, but we just made it that way so that we all agree on the same answer, the same output, so we only get one answer instead of a multitude of answers that we might get if we varied the order every time. Similarly, with what we're going to do here. On your paper, you were supposed to restrict. Well, we've done this before, right? We've done this before. What do we do when we want the inverse to be a function? Because right now the inverse is not a function. What do we focus on when we want the inverse to be a function? Shane? Yes, we restrict the domain of the original function. What do we need this original function to be in order for the inverse to be a function? Colin? Yes, we need the original to be a one-to-one function. So, that's what you were supposed to do it last night. If you didn't, do it now. What would you restrict this blue curve? How would you restrict the domain of the blue cosine curve so that it is a one-to-one function and therefore the red function, the inverse, will be a function as well? Talk it over.
You have to do 0 to pi.
Yes, the whole period. I did negative pi to pi.
Time were we at?
6 minutes. No, it can't be. It has to be half.
If you can hear me, clap one.
0 to pi.
All right. So, what did you come up with? How do you want to restrict this domain? Bailey?
It can only be pi long.
Pi long. Is that a character from Star Wars?
It's the main function.
What could be pi long? Give me a restriction. Tell me what the restriction
0
is.
to pi.
0 to pi. All right, so I'm going to restrict the domain of the cosine curve. You can see on the screen that the blue curve is shrinking, and I'm stopping at 0. I'm trying to stop at 0. It's a little touchy. That's close enough. All right, and then we'll restrict this to stop at pi. How many agree that that is a one-to-one function in blue? And if you look at the red, it's now a function. That worked. Could we keep any more of the blue curve? No, we couldn't, because as soon as we extend any further to the right, it's going to fail the horizontal line test, and as soon as we extend any further left, it's going to fail the horizontal line test, and then the red curve would fail the vertical line test. So I agree. Is that the only one-to-one section that we could keep? Sammy, give me another one. 1 pi to 2 pi. 1 pi to 2 pi would have worked. You're going to say as long as it's what? Half a cycle? How about if I went from negative pi over 2 to pi over 2? That's half a cycle, but not acceptable, right? Because it fails the horizontal line test, so you have to be careful. But we've kept as much as we can, but there's an infinite number of those that we could have kept. How about from negative pi over 2 to 0? That would have worked, right? Actually, no, I'm sorry, negative pi to 0, right? Negative pi to 0 would have worked. What do we do, Allison? Yeah. What?
She's looking out for you.
Oh, you're just watching my back. Thank you. I think we started.
Yeah.
Yeah, okay.
Hey, Corey.
Nice. So, you said hi to Paige, too, because I think Paige will be watching it from second grade.
Hey, Paige.
So anyway, the concept here is that there's infinite number of those sections we could have kept, but we have to agree on something, right? Matter of convention, just like the order of operations. And the convention that's been agreed upon basically tries to keep it, include 0 if you can, and stay as close to 0 as you can. And in this one, you can say, yeah, but we could have kept the left side. You're right. So if you think about it, we kept, instead of starting at 0 going this way to rotate, we went the positive direction. So that's what we did, and that's the convention. Okay? We're going to keep that section of the original cosine curve so that the inverse is a function. And this is why your calculator can give you one output when you ask it to calculate the inverse cosine. It's only going to give you a value in here. Not out here, not down here, because we restricted the domain. Why do we like that? Because sometimes we want it to be a function. Sometimes, like on those first 3 problems we did, it could just be a relation. We can list all the solutions. Okay? Question, Austin?
Why did you say you can't cross over y? Or like,
Cross over what?
like x equals 0?
You could have. I said you could have. You might have said that, well, why don't we keep that section? That would work. you're right,
Even if it's like midway through,
midway through.
like halfway through the column on both sides.
Oh yeah, you can't do that.
Why
You
not?
can't
though?
keep this because that's not one-to-one. And if you turn it sideways,
Oh,
it's going to
okay.
fail the vertical line test. Yeah. So you have to keep a one-to-one section of the graph. Okay. All right. So what I want you to write down, you can do this either on the worksheet that you had for homework, or you can put it on the back or on a separate sheet of notes. But this is important stuff that you want to get down. We're going to look at, let's call it f of x is cosine x, and then over here, the inverse of f of x is the inverse cosine of x. And we're going to look at the domain of range, and we're going to look at the restricted values so that these are functions. Because when I use the f notation here, this is a function. This doesn't have to be a function because it's just the inverse of a function, but we're going to make it so that it is a function. Okay. So what is the domain of function f, and what is the range of function f? Well, we just restricted it. We just restricted it. Who told me that? I forget who it was even. Who told me to restrict this? Bailey, what did you say it was restricted to?
0 to pi.
Inclusive or exclusive?
Inclusive.
Inclusive. That's 0 to pi radians, right? That could also be written as 0 degrees to 180 degrees. It'd be the same thing, depending if you're in radians or degrees for the angle. The range is what? Emily? Range. Bottom to top. Blue.
-1.
Yep, -1 to 1, inclusive, right? How would that change if I go to degrees? It doesn't. It doesn't. There are no units on the ratio, right? So it would be the same thing, all right? So here's something, a couple things that are very important. Number one, the input here is an angle, and the output here is the ratio. Now, we've known that ever since we started this stuff, but a lot of people just stop thinking about that. Don't stop thinking about that. That's important. What's the input? What's the output? When we switch it, when we go to the inverse, of course, the domain and range flip. X and Y switch. So you just have to reverse it. The domain of F inverse is going to be what the range was for the original, and of course, the range of the inverse is going to be the domain of the original, either 0 to pi inclusive if it's radians, or 0 to 180 degrees if it's in degrees. And what happened? Well, of course, they switched. So now the input is the ratio, and the output is the angle. Any questions on that? I'd also like you to put a little picture that goes with this, because this is important when we'll be getting into where do you find these angles between 0 and pi radians, or between 0 and 180 degrees? Where do you find those in standard position? Where do you find those angles? 1 and 2, that's important. Okay? So we're going from quadrant 1 to quadrant 2, inclusive, right? So we could be on the axis, but we will never get an answer that's in quadrant 3 or 4 if we're using inverse cosine on the calculator when it's a function, right? So let's talk about that briefly. We'll talk more about it as we go. When you see inverse cosine, inverse sine, whatever it is, written down in a math problem to start with, it's there from the beginning. In general, you're going to assume that that's a function. In other words, you must assume that these restrictions are in place. If it's a problem like we started with, 1, 2, and 3, where it just says, find the angle whose cosine ratio is this, they didn't write down the inverse cosine, did they? You never saw that written down. On those problems, you just treat it like a relation, like we did, and we get infinite number of solutions sometimes, or multiple solutions. So that's the general rule. If you see it written from the beginning, assume that it's a function and the restrictions are in place. Otherwise, it's just a relation.